Think you could knock open your CPU and point out all the different parts on it? Sarah?
How big would a circuit like that circuit be with our technology?
Good question. That would be, I can't give you an exact number, but it would be far too small to see. Because what we do is, so I'll go back a little bit to where we looked at our transistors. The way we manufacture these is we take a large silicon wafer. So it's a really big, or not really big, but big in computing means we can see it. It's a big chunk of silicon doped one way, and then we just etch on it a bunch of these different channels, and then stick on a bunch of these metal oxide gates. And we can make that very, very small, in the order of 40 nanometers. In fact, I think Intel is getting it down to 20 now. So 20 nanometers for one transistor, and each gate takes, like the NOT gates, I showed you one with one transistor. In reality, they take two because transistors don't behave as nicely as I made them out to in this class. And an OR gates take 4, I believe. So you can kind of do the math from there, right? Add 40 nanometers across. It's about 100 nanometers long. And you can do the math, figure out how big it would be. It'd be very small, on the order of micrometers, right? But yeah, so that's how we take those transistors, put them all on a little chip, and then we can basically print metal wires across that will connect them as we need to. And we can implement, wrong way, and we can implement our CPU based on that. So that's our basic CPU. Any other questions about it? Okay, so we have our machine code in our main memory selected for by IP, sends it to here. How do we write our machine code? We could write binary like that, but that's really boring. Humans aren't good at reading binary. It doesn't work well, and like most people hate programming as it is. If you guys had to type with just zeros and ones, you would go batty very quickly. So that's a first generation language, is machine code. We go ahead and make what's called a second generation language, which we call assembly. And assembly is a one-to-one mapping that's easy to read. We've seen a little bit of it before. Add C, A, B. Set A plus B, send it to C. That corresponds one-to-one with our machine code. We know what add means, we know what C means, A and B, and we can just get the binary code from that, but it's a lot easier to read than 11 or 0010001010, right? I made a mistake there. That shows how cumbersome it is. So yeah, it's right here. I did not need to think of it in my head. So conversions one-to-one makes it a very simple process, and that's why assembly language was one of the first languages to come out. It has so much benefit, so much more readable, but it's really easy to compile. One thing that we'll have to understand for assembly is hexadecimal. Does anyone know what hexadecimal is, or think you know what hexadecimal is? Sarah?
It's like base 10 or base 2 or base 16.
Yeah.
You add letters after you end at 9.
Exactly. Yeah, so for those who didn't hear what she said, it's base 16. So you had 0 to 9 and then A to F. A represents 10, F represents 15. And we have this nice mapping right here, right? So F15 goes down here. Why do we use base 16? Why can't we use base 10? Any ideas? Seeing a couple thoughts. Sarah, I've heard from you a lot. Sir, I forget your name? Pardon? Boom? Yes. Exactly. It's easy to convert to binary. Why is it easy to convert to binary? Because 16 is a perfect power of 2, 2 to the 4. And look at this. There are 4 binary digits to 1 hexadecimal digit. That is not a coincidence. That's because we have 16 different possibilities in 4 binary digits, and we have 16 different possibilities in hexadecimal digits. 16 in binary takes 4. Why doesn't it work in 10? Well, 10 is 2 to the power of what? About 3.3? How would 3.3 binary digits to 1 decimal digit work? it doesn't work, right? So we'd have not a one-to-one conversion of digit to 4 digits. We'd have to carry over a certain value every digit that we convert. In fact, there is an algorithm for pi. It can calculate the hexadecimal digit at any value. So we can say get the millionth hexadecimal digit without calculating the first 0 to 999,000. It does that for hexadecimal only. We can't convert to decimal because to convert to decimal, we need to have every other hexadecimal digit before it to get to that millionth decimal digit, which wouldn't be millionth because there are more decimal digits than hexadecimal, right? So decimal, hexadecimal do not play nicely together. Hexadecimal and binary do. Make sense? So we have that one-to-one mapping, 0 to f. So 0 by 0x, x stands for the x in hexadecimal. 2a. Anyone want to take a crack at what 2a represents? Okay, I've seen both of you. Sir, remind me okay, I know your name. Francis? Julie. Yeah. So we have 2a is what? Sorry, I can't quite hear you.
So that stands for 12.
So I heard 12. I think you're going the other direction. So if 2a were decimal and you were getting hexadecimal, I don't know how a would work there, then it would be around 12. Sarah?
I think I multiplied.
That's okay. Hearing a couple banter over there? 42. I think so. Yes, it is 42. Yeah, that is the answer, 42. Everyone know what I'm getting at there? Hitchhiker's Guide to the Galaxy, look it up, good book. 2a, so how do we get 42? For those of you who haven't quite got it yet. 2 times, this is in the 16s place. 2 times 16 is 32. A is in the ones place, A represents 10. So 32 plus 10 is 42. Yes, remember your name? Pardon? Edward. Yes. Edwin.
What does the 0x represent?
So the 0x is another way of saying it's hexadecimal. So we could put that subscript 16. In computing, since subscripts don't play well with basic text, we put 0x to represent hexadecimal. 0d is decimal, 0b is binary. You sometimes see 0o for octal, which we won't get into. But yeah, so it says it's hexadecimal, and you'll see that fairly frequently in low-level computing. Yes, remember your name? Pardon? Judith? Yes. Sorry? Oh, okay, so yeah, it's not 0 times. Sometimes it's pronounced that way. It's not multiplying by 0 because that's just stupid. It's saying 0 is just carryover from ages gone by. It just means this is the start of a base representation, and then x says it's hexadecimal. So the 0x says, interpret this as a hexadecimal number, right? Because I could say give you 11. 11 we think is 11, but it could also be 17 if it's 1 for 16 plus 1 for 1, right? So 0 by, or 0x11 is 17 decimal, 0d11 is 11 decimal. Yes, remember your name? Sarah, yes.
The base was 2. It was like 2, 4, 8. Like
Yep.
That. But now it's not like 16,256.
It is like 16,256. Yeah, so at base 16, we multiply by 16 each time, right? And notice that 256 is 2 to the power of 8. Pardon? Yeah, so the bases are times 16 to the power of initially 0 for the ones place, 1 for the 16s place, 2 for the 256th place, etc. Any questions on hexadecimal? So yeah, the question was, how do we get 42 from 2a? So this is the ones place, and this is the 16s place, right? So 2 in the 16s place. So Jenny, what would 2 in the 16s place represent? So like 2 in the tens place, say, in decimal, is 20, right? And 20 is 2 times 10. So what would 2 in the 16s place represent? 32, yeah, 2 times 16. And then A, we can look it up here, is 10. And 10 in the ones place is just 10. 32 plus 10 is 42. Make sense now? Any other questions? No? Any questions on assembly and how it converts to machine code? Awesome. So let's take a look at a very simple program. The one thing on that slide I forgot to mention is labels. Labels do not convert to memory. This main colon is not corresponding to any sort of machine code opcode. It just says, it tells the assembler, take main, anywhere we say main, insert this memory address. So the memory address of move AX to 4, that's 0. When we have main here, this is going to be 0. So jump to 0. And the same with loop. So labels do not get converted to machine code. They get converted to labels elsewhere in the program, and they get stuck into the value as constants. So it makes it easy to work with addresses, right? If we say move to, or set IP to 0010, what does that mean? If we say set IP a loop, that makes a lot more sense. So the second thing to think about is the stack. In main memory, we have what's called the stack. So a stack is like a queue, right? So a queue, you have the first in is the first out. A stack, the first in is the last out. So like a stack of pizzas. Put a pizza here, put a pizza here, put a pizza here. The one we get off first is the one on top, right? And that's used for functions in argument passing. So we say, I'm going to give, if you have, say, an add function, add a plus b. You put a and b on the stack, call the function's going to pop these values off. It's going to do the adding, pop the sum to the stack, and then you get it called back, and you push the sum to the stack, then you pop the sum off, and you can use it. So that's a stack. So we can use that for a very basic assembly example. This is a stupid program, doesn't do anything useful, but it illustrates the point. So we first move AX to 4. Move is like set. So after this is run, AX equals 4, right? Remember, AX is that register. And then loop, this is just a label. It labels this memory address of push. We then push AX to the stack. So AX is now at the bottom of the stack. Inc AX. Yes. So push AX says take the value in AX, put that value on the stack, right? When we say pop BX, it means take the top value on the stack, put that value into BX. Okay? So push is we just got a pizza delivered, put it on the stack of boxes. Pop is we want to eat it, take the top one off. And whatever variable we pop into is the person who eats that pizza. Right? So inc AX, inc stands for increment. It's like add, just add 1. So we add 1 to AX, so AX was 4, it is now 5. Push AX. So we just pushed 4 to the stack when AX was 4. Now we incremented AX, so we're going to push 5 to the stack. So we have 4, 5. Okay? And now pop BX. So we're going to pop 5 into BX. The value of BX is now 5. Pop CX. So this is now popped, off the stack. And now we have just 4 down here, pop that into CX, and that gets popped off the stack as well. So now BX is 5, CX is 4. Note that it's flipped, because the stack is flipped. It's first in, last out. CMP. This is something that happens in x86. So x86 is what runs on most Intel processors. Compares the two. It says compare BX to 7. And we have a little register. It's a 1-bit register, like just a latch. If they're equal, that compare operator is going to set it to a 1. If they're not equal to, it'll set it to a 0. And for binary equality, we just use that XOR gate, right? So XOR gives us a 1 if they're not equal, and a 0 if they are equal, right? And then we can AND those all up and see if it's equal to 7. So we compare bx to 7. Is bx equal to 7? So we just popped the value 4 into bx. So what's compare bx going to set that flag bit to? It'll be 0, right? Because we compared it, it's not equal, so it's 0. And this command is jump not equal. So that says if it's not equal, we're going to jump right up to the top here. I made a typo, this should say loop. So my bad there. Jump not equal to loop. So loop doesn't exist in the program, it says this memory address. So this memory address, assuming these are one address per command, will be 0001. So this it converts into machine code of jump not equal is just the opcode for jump not equal 0001. So we replace loop with the actual location of it. If it's not equal, we jump up to loop. And then we increment AX again. So we repeat this until BX that we've popped from AX that we've pushed after incrementing is equal to 7. When we're done, we're going to call exit, call, yes. So, yeah, so JNE stands for jump not equal. So if the last comparison we did, because it sets that flag bit, if that is a 0 for not equal, then we're going to jump up to loop. I made a typo, it should be loop. Yeah. If we jump up to main, this is never going to terminate because it's always going to set AX to 4. Yes? Sorry, can you speak up?
When we increment binary code, we increment it by 1.
Yeah. Yeah, so increment is defined to add 1, so it's just an adder circuit, except we hardwire 1 to one of the inputs. Yeah. Okay? And finally, call. Call is a special kind of a function. It says we're currently in our own code, but this program normally runs within an operating system. So we're going to say jump to external operating system code, and the operating system is going to clean up our program nicely. So that's a basic assembly program. Very stupid, doesn't do anything useful, but it illustrates the point. That makes sense? So get rid of that. Let's give it a shot. So go ahead and open up your shared folder. And I will open up mine and find this omnicalcs.exe in it.